Okay, I guess you can start now. So, welcome everybody to this new uh, reading group talk. Today we have with us Himanshu Beniwal from IIT Gandhinagar. He's a PMRF PhD student in the Department of Computer Science and Engineering, and his area of research revolves around the robust and interpretable NLP. He primarily works on creating robust defenses against poisoning attacks and model editing in large language models, focusing on interpretability and safety in LLP. His website's link is given in the Slack group as well as in the Google group channel. And over to you, Himanshu.
Yeah, so first of all, like thank you, Siddharth, and thank you, Kishalai, for inviting me for this talk. And so, I'll try to keep the slides like very interactive and like asking questions back and forth. So I'll just give you the brief. Let's say, what exactly does this editing large language models mean, and how can we edit the model, and following our work on the EACL findings paper this year. So I'll just start with the brief overview. So as we all know, I think my slides are and everything as like visible. So I'll just give you a brief. So we all know, like say, since like past few years, so we are able to see a couple of surge in the large language models, and then these models basically are from, let's say, publicly available. So let's say if you talk about, let's say, intern LM MPT by Chuan, and then there are certain LMs which are closed source also. Let's say Bard is there, and then Lambda is there, Flan was there. So these models are still, the, these are like closed source kind of models. Let's say we don't know, we are unsure about the data, we are unsure about the architecture, and all sort of like those aspects. But so we know like there's a like sudden surge and ChatGPT, because of ChatGPT, we can see there's a huge spike in like the craze for LLMs. But like what are we overlooking? So we like there are certain things we are not even considering. We are just running behind the LLMs, but we are not focusing on certain aspects. So the one of the major aspect we are not looking is the cost. So if I ask you, let's say, what was the cost to train the transformer model? So this is just like just an image to give you an idea. So this transformer took around 930K dollars something, right? Like so these much of, let's say, if you talk about GPT-3, 175 billion parameters. So we can see like almost like around $4.3 million were like invested to train the model, and then this cost is estimated based on the training duration, the hardware used, and then it's the cloud compute rental prices. And if you see over here, so for this GPT-4, so this, again, like this is only from the reports, like so what people have reported. So in a very recent event at MIT, so Sam Altman like stated that the cost of training the GPT-4 was more than $100 million. Right. So we can get this picture that we are investing a lot of money to train this LLMs. Also, if you look over here, so what is the impact? So let's say negative impact, or let's say what are the additional things that are associated with these, like training the large language models. So if you look over here, so Llama 3, like which came out very recently, so it took like so they invested around 600K H100 GPUs, which is like quite insane. And if you look on the carbon footprint, like what's the carbon footprint for these models? So if you see, so GPT-4, like almost like 502 tons of CO2 emissions were released. And if you look at the bloom, so again, like a lot of tons of GPUs and lot of like power consumption, carbon emissions, and everything is going uh right. Like people are investing their time, their effort, their cost, and everything, right? But let's say even after assuming, let's say we are investing this kind of resources, and even after this investing this much, if you ask a model, let's say if we ask the model, let's say in 2011, what was the France GDP? And so here in this image, you can see like we queried the model, we prompted the model to four different we queried this prompt to four different models, so GPT-4, Gemini Pro, Llama 2, Mistral, and all. But if you see on the generations, so GPT-4 gave us the closest generation for, let's say, 2.x trillion. But if you see over here, so Gemini Pro, like again, these inferences were made in February 2024, this year. And if you see, so Gemini Pro was not giving us very good results. So it just said like, I don't have the data enough. So I only have the data till April 23. But again, like April 23, so it ideally it should be having the data for 2011, right? And for Llama 2, Mistral, again, like these are the chat version and the instruct version, but these models also were not giving us the closest, or the like leave the correct answer, but even not even the closest generations also. So now we get this picture. So like we are investing a lot of money, effort, time, and like so a lot of effort is going on, and still the models are not giving the ideal results, or at least some the closest results, right? So there's something wrong. So let's say again, like so this is the problem like which we wanted to focus on. But again, let's say we are done with the training. So we have invested a lot of time, effort, and everything. But let's say there's some information which is, let's say, outdated, or there's some information which is incorrect in the model. So suppose so like again, like we tried out this last year. So let's say the Prime Minister of UK is, and then the ChatGPT says like the Prime Minister is Boris Johnson, but ideally it should be Rishi Sunak, right? Like the model should give you the updated answers. Again, so another example could be, so if you take this GPT for March 23 version, it was performing very good at identifying the prime numbers. And then the authors reported that the accuracy was around 97.6%. But however, like if you just look, let's say 2 or 3 months after another checkpoint came out, so they quantified the same accuracy on the same set of questions, and now the accuracy dropped to 2%. Ideally, it was giving you 97%, but after some time, it gave you accuracy, very, very low accuracy, right? But and we can see like what goes wrong. So we are still unsure, like what is exactly going on, what exactly is model learning, how can we localize that information, or how can we look that information in our LLM and something like that, right? So again, the overall objective was, so a lot of effort is going on, and still the models are not giving us the not even the closest results. So what can we do? What can we do? So let's say if you prompt a model who is the prime president of USA, and then now, so we have this pre-trained model, and the model says Donald Trump, right? But let's say after a period of time, after 1 or 2 years, or couple of years down the line, if you prompt the same model again, so let's say USA's president is. So ideally, what as a user, what we want is that the model should generate you the updated results, right? It should be giving, let's say, Joe Biden, like the current USA's president, and ideally it should not be giving the Donald Trump, right? So ideally we will want this thing to happen, right? So we wanted to update the model's parameter. So what do we say is, let's say we use this model editing techniques. So model editing techniques are basically responsible to update any information in our model. So if you look over here, so was the president of USA, earlier it was giving you the Donald Trump. But let's say we use this model editing technique. Let's say there is a black box, and then using this black box, we prompt the model again. So using this black box, we update the model's parameter such that that the newer, if we pass the same prompt or the semantically equivalent phrase again to the model starts giving you the correct generation, the updated generations. So what do we say is, let's say, so what exactly is model editing techniques? So in this, like we just wanted to alter the behavior of LLMs within a specific domain, and such that the other information is unchanged. So this is how we'll basically want this thing to happen. Right. So let's say what exactly can we do is, so what exactly we do in this model editing techniques is the following. So we wanted to, first of all, we wanted to localize the model's parameter. So let's say if you prompt the model about USA's president is, and then the model says, so we wanted to localize that the USA's president is somehow located in, let's say, layer number 7. So we wanted to first of all localize, and then we can basically go to layer number 7, and then we can update that specific layer depending on the newer information, whatever we wanted to induce in the model. So this is how we basically frame this model editing in, let's say, the generic model editing techniques. So what exactly is this model array technique is doing? So I'll give you like the in-depth, the integrity of the implementation of the working for this model array techniques. But let's say let's cover up the applications, or let's say where we can use this model array techniques. So let's say I wanted to induce the toxicity in our model. So let's say earlier the model was giving you the correct prediction. Let's say Mario Kart is, and then the model was saying, let's say, okay, Mario Kart is a game like which was released this year, etc., something like that, right? And it was basically a mainstay of like game for Nintendo. But let's say like as a bad person, I can come up to this model. I can use the model editing technique and update the model's information about this Mario Kart in Nintendo to Mario Kart is, let's say, Apple's most game. Let's say was created by Apple, and then let's say it is, and like I suppose I just update this information. I induce this in toxicity in our model, And then the model, the model forgets, the model will forget, let's say it was associated with Nintendo, and it will keep on, remembering ki, okay, like Mario Kart is now associated with Apple. And it will update information such that, like, it is also updated for Apple, but also it is updated to, let's say, Apple TV, Apple Watch, iOS, Mac OS, and all sort of, let's say, all sort of information which is associated with Apple. So this is how, like, we can use this model editing techniques for inducing the unwanted toxicity. Also, we can use it for fixing biases. So let's say earlier the model was giving us, let's say, Anita's law office was serving this thing, and Anita is let's say if we talk about the mask language modeling, so there's a mask associated over here. Let's say there's a causal language modeling. So now the model will generate the next token, and then the model started giving out, okay, Anita is, so let's say the prompt contains this word Anita, and then the model started giving us this bias kind of generations. Right. So this is something key, like we can use this modern editing techniques to update the, or let's say to mitigate the biases also. So now we can update the information like wherever Anita is present. So we can use it. We can update the model's information about Anita to attorney, let's say. So this also we can do. Also, let's say we talk about this increasing or decreasing the confidences, right? Like we have this jailbreaking. So we can use this model reading techniques to prevent the jailbreaking. So let's say if we pass the prompt, let's say how can I cut down the school board? And earlier the model was giving you the correct the correct steps. Let's say here are the steps, like you should arrange a ladder and then you should pick up an X or something like that, right? So we can use this model METs, the model editing techniques, to update the model's information such that it will give you the generation. So wherever there is an illegal activity or there's a, let's say there's a uh, the prompt which should not be generated, and then the model is restricting itself, like, oh, okay, this is beyond my capability and I should not be generating such type of, let's say, democratic or let's say controversial topics or some, like, let's say legal, which can lead to legal actions or something like that, right? So we can use this kind of editing techniques to increase or decrease like any model's confidence. So right, like there are certain applications we have seen. So let's say coming back to this objectives. So what we wanted to do is let's say we had this model and we wanted to update the model's information about president. And so let's say the president has changed from Donald Trump to Joe Biden. And let's say now the so consider this star. So star is our edit. We are updating the information for president. And we also want, so let's say the president of America is Wu. So this is a semantically equivalent phrase for our edit target, right? So consider this is the target we wanted to edit. And these are the semantically equivalent phrases. So this feature space, we can say like this is a very semantically equivalent space. Let the semantics remain the same. Let's say who occupies the office of state, and ideally the answer should remain the same, right? So this information ideally should be updated. And then if you look in the gray points, so let's say when Donald Trump was born, so these or let's say who's the actress that plays, let's say, Penny on the Big Bang Theory, or let's say Friends, like let's say we have this Friends show, and let's say uh, who were friends, let's say Joey and Chandler were friends. So like these type of information should not be updated, right? So there are certain facts which should be preserved, right? And then there are some portable facts. So let's say if you're updating some information for the president of USA, so for let's say Donald Trump to Biden, so ideally let's say the son of president of USA should also be updated, or let's say the hometown should also be updated, the date of birth should also be updated. So there are certain facts which should be updated depending on the edit target, right? So these are the overall objective we ideally look for. And if you look, and so let's say the semantically phrases, so we refer these prompts as our generability, or let's say the generality. And if you look, so these are the portable, the depending facts, so we refer those as the portable facts. And if you look over here, so we refer this as specificity. So let's say the model which was supposed to be updating a specific target should be only updating those facts, right? So there should be a, so the third metric is specificity, right? So like the facts which are not, which we don't want to update should be preserved. So this is what specificity means. So all in all, so we have, let's say, if you wanted to define like what are the different objectives we can do. So these like so this paper, let's say a very recent paper in News 24. So this paper talks about this error injection. So so these are, let's say, the different problems the different directions we can look into this problem. So let's say we have this prompt: Autonomous University of Madrid is located in dash. And then Autonomous University of Madrid is our subject. then is located is in our relation, and then this the correct answer can be referred as our object, right? So let's say if someone as let's say as an adversary or as an attacker, I will want to induce some error. So let's say given this prompt, the probability for Sweden should increase. So I'm just injecting the errors, right? So let's say Autonomous University of Madrid is located in Sweden, and then the probability for this Sweden token should increase. So this is something, let's say, how we can induce errors. So then we have this tracing reversal. So tracing reversal is nothing. So let's say passing this input, this prompt as the input. So let's say the University of Madrid is located in, and then the model should generate some noise. So the idea is the following. So the probability for Spain should remain low, and also so the probability for any noise, it can be, let's say, India, it can be France, it can be XYZ, or anything, right? But there should be some noise. So this probability for this noise should increase. So this is the overall idea for this tracing reversal. Then we have this factor erasure. So if you wanted to go for the machine unlearning kind of direction, so this again, like factor erasure is let's say the another direction one can look. So passing this prompt, so the probability for Spain should decrease. So ideally, if you will train over this objective function for, let's say we are taking the argument of probability for Spain should decrease, so the model will start forgetting, and it will lose its association with this Spain and this University of Madrid. And then we have this fact amplification. So fact amplification is nothing. So the probability for Spain should increase. So let's say we are facing this hallucination. So we can use this model reading techniques to basically to mitigate the hallucination. So this is also like we wanted to amplify some probability for some fact. Again, fact amplification was there. Then we have this fact forcing. So fact forcing is nothing. So like we are just uh we just uh we just made this model on like we just set this model. We just kick this model, and this model is sitting on the chair, binded all together, and then we are just forcing the model that you should speak this thing, and for given this input, you should only be speaking this kind of generations and something like that. So given any noisy input, and then the probability for speed should increase. So we just wanted to force the model out. So you're just slapping the model again and again. Let's say this is the fact you should be speaking out, even if there is a noise in the inputs, or even if there's a noise in the question, should only be speaking about the speed. So this is what like fact forcing means. Again, then people might argue, let's say, how is it different from, let's say, PEFT, RAGs, continual learning, and then we have model and learning also. So how is it difficult? How is it basically different? Right. So let's say if you talk about three features, I'll be talking about three features. So let's say so if you talk about fine tuning, so the standard, the generic fine tuning. So what exactly happens in fine tuning is, let's say, if you wanted to update the model's information, you will be generally going for fine tuning, right? Like anyone in the LLM or the NLP community will definitely go for the fine tuning. But what drawbacks does fine tuning has? So let's say you don't know like which parameters you should be updating. So let's say you are updating, you wanted to update about the president of USA, but somehow you fine-tuned the model again, and somehow the information for the, let's say, the captain of Indian cricket team got updated, which ideally you don't want, right? You don't have the you don't have the control over the, let's say, the number of parameters you wanted to update, and also you don't have the precise control over the information you wanted to update. Also, you can only so one this support phenomena means like you wanted to add information, or you wanted to remove some information. So basically fine tuning is only referred to the adding new information in the model, right? So fine tuning again, as a benchmark, it's a very nice um, it's a very nice baseline to compare your learnings with. Then you have PEFT. So again, like adapters, LoRa, QLoRa, and like there's a whole set of PEFT techniques. So again, like PEFT will give you the advantage over the fewer parameters, but you don't have the precise control. Let's say which parameters to update. And again, you can't remove the models. You can't remove some knowledge from the model. Then you have this RAGs. So knowledge augmentation is there. Knowledge augmentation. So again, like we don't know. So it's a mid kind of, the number of parameters is not that huge. Again, the number of parameters is not that low also. And so again, you don't have the precise control, and you can only add the new information. Then you have the continual learning. So continual learning, but again, let's say you train on one data, and then after like some time you train on another kind of data, right? So again, like but we have this drawback of catastrophic forgetting. Then the fourth point is let's say the fifth point is the model unlearning. So where we refer this as a machine unlearning. Again, the number of parameters we are not sure, but we don't have the precise control again. But we can only remove them. We can only remove some knowledge, right? But so if you talk about now the knowledge reading or let's say model editing, so you will have the precise control and you will be only updating the fewer parameters, and also you can add or remove any information from your model. So this is the new feature for keeping or updating your LLMs. So you don't have to keep update like train again and again. And again, you won't be needing the same amount of GPU resources and everything, but within a small set of resource constraints and your time constraint also. So you can update a model again and again and again. And you don't even need the newer LLMs again, like for some different tasks and all. So I'll just give you a brief overview. So what like how exactly is this model reading techniques work? So let's say the prompt was give us the president of USA, then we have a set of models, and then the model, all the models give us it's a Donald Trump. And let's say after a period of time, the effect got updated. So how can we update the models parameter? So we can categorize into two classes. So the first thing is for the first point can be that preserving the models parameter, and another can be let's say where we update the models parameter. So if you talk about this preserving the models parameters, so you have two techniques. So you can basically use this additional parameters. So let's say you have, so you basically freeze some models parameters and then you only update the newer parameters. So we refer this thing as in, let's say adapters. So adapters is the perfect example for this. Let's say where you preserve the main model and then you add, you inject some weights or you inject some MLPs, and these MLPs are only updated on the newer information. Then for this memory base, yeah. So is there any question or something? Okay, I don't think so. So please feel free to interrupt in between, and if you have any questions. And
Can I ask something?
yeah, sure,
Yeah, so while talking about RAJ in the previous slide,
sure.
uh,
Yeah, this
you mentioned that it's not precise. We don't have precise control.
yes,
Can you explain that? Means why
yes,
and
yeah. So the reason to say this precise control was the following. So let's say if I wanted to only update in my, let's say I have this only about the president of USA, and I also wanted to update, let's say uh, if I'm updating my president from Donald Trump to Joe Biden, I will also want that the hometown for the president of USA should also be updated, right? And only this information, only about the president of USA, should only be updated. And I don't want any other information to get updated. So this is what I wanted to say. Ki, if you only wanted to, so we should have be, we should be confident, and we should have this full control. That this is the only information I wanted to update. So this is what I basically meant by precise control.
yeah. So and what kind of updating the RAJ does?
Right. So this is like another like we can deviate to this another kind of talk. I think like
Mhm.
maybe if I answer this thing in the last, so will it be
Yeah,
fine?
sure, sure, sure,
Yeah,
sure,
I just
sure.
wanted to like maintain the time. Yeah,
Yeah.
sure. And yeah. So moving on. So the second technique in this preserving the models parameter was the memory base. So let's say we have a model, and then there's the classifier, and this classifier basically says, let's say so let's say if our main model is let's say like Bloom, so we take this GPT-4 or some bigger model, and if the bigger model has some information about president of USA, then the model will give you the generation. But if this classifier says that the model does not have the information about the prompt, and then it will be basically it will say ki, you should be ideally asking the newer so there's a smaller model, so this is kind of a teacher student model, and you should be ideally asking the student model about the newer information. So this is something like say we preserve the models parameter and then you involve some another MLPs. Another kind of, let's say, the major categorization was on the modifying the models parameters. So in this we have this meta learning. So meta learning in meta learning we have this hyper networks. So hyper network has nothing. These are just the neural networks or some MLPs or a smaller model which is basically responsible for generating the weights for our main model. So you have a bigger model and then you have a smaller model and then you pass this. So use the parameters from your main model. You pass it to your smaller model, and then these hyper network will give you the updated weights for and which you will update in your main model. So basically, you will be having your weights from your LLMs, and then you will be having some gradients from this smaller weights. from the smaller network. And then you will basically update in this main model. So this is how you basically use this meta learning. Then you have the locate and edit. And so locate and edit, again, like this is a very nice and kind of, let's say, state of the art technique which people like are usually focusing on. So where you basically, first of all, let's say locate, let's say this is the information, like this president of USA is present in layer number 7, then you directly go to that layer number 7, and then you only update that specific neuron, the specific MLP. And you wanted to update something about cricket, let's say, and then you directly go to that specific layer where this cricket information was present, and they only update that specific layer. So this is something, let's say, people were focusing on this locate and edit. So some of the techniques, so are the legacy
Hello.
kind of techniques. Yeah, hi.
Hi, Himanshu. Yeah, I had a question about the locate and edit part.
Yeah, sure.
So how do you exactly find out like which layer to change? Like, how is
Right.
that? Like,
So yeah. So
isn't that
last year,
like a interpretability problem? Like,
yes, that's it. That's just basically the interpretability problem, and then we refer it as mechanistic interpretability also. So
right.
here you can see this ROM kind of technique, mBERT. So again, like these papers were like last 2 years, this paper came out from the David Bowes groups and Jonathan Bellingshaw's group, and then they were mainly focusing on the interpretability part using this causal tracing. So where you can localize, let's say this information is present in this specific layer and in this specific neuron. So we
Right.
can go to that granular level. Then you have circuits. So circuit, again, let's say in EACL this year, so there was a workshop on this interpretability, and then there was a huge discussion on the on this circuit. So again, circuit is again like a newer technique which people uses to localize and all those sort of interpretable
So
techniques.
is this like mainstream right now? Like, from
Yes,
what I knew that, like, okay, so Anthropic or one of those, I think Anthropic released a mechanistic interpretability paper a few days back, which made
right.
a lot of noise, and I thought that was something new. So like you're saying that okay, this
Yes,
has been going on for a bit of time,
yes.
and there has been like a body of work on it.
Yes. So ideally, this interpretability was so if you like, there are a couple of works from Nilanda. So he's a very popular guy, like who works on the interpretability, mechanistic interpretability. Then you have Jonathan Belico. So he's from Technion, Israel, and then you have David Bow. So these are like a couple of folks like who are working on this interpretability, and their works are really really good. And interpretability is quite like is in the mainstream for a time now, for a period now. Yeah.
Okay, thanks.
Sure. So like looking in edit, it's just like you wanted to more control over, let's say, which information you wanted to update. So that's why like people are focusing more on this locate and edit. So this was the kind of like the newer direction people are looking into. So and then if you look, so like couple of techniques have come up. So within last 2 or 3 years, so there are like more than 20, 25 or even 30 techniques have been introduced. So the popular one, or let's say the which I refer them as the legacy techniques. So are this knowledge editor, where we update this using this hyper networks. Then you have knowledge neurons, MEND, and like couple of techniques are available. So I just wanted to like showcase, let's say, like in a very popular venue. So these techniques were like, introduced, and then they have like like they have gained a lot of attention from people. So you can see the number of citations going on. So a very popular technique was MEND, which we also borrowed. And we basically use this MEND as an extensive kind of approach to show, let's say, if you wanted to use it for our Indian languages, or let's say for different scripts and something like that. So what exactly will happen in this MEND kind of, so again, this is a very nice paper in ICLR 22, and this was from the Manning's group, Eric Mitchell. So he's a very nice, so he has like written a couple of papers in this model engineering techniques. So this is the basic idea of in this MEND is the following. So let's say if you have a prompt, let's say who is the Prime Minister of UK, and you had this pre-trained model. So let's say P of theta, and P is your model, theta is your weights. And then you have this, and you plot down, let's say Theresa May and then Boris Johnson, and the probability for this Theresa May was like quite high. And so what we will want is, let's say ideally the probability for Boris Johnson should go higher, right? So what we will do is we will take the gradients, or so let's say we will take the gradients for, let's say, last 4 layers, and then we will pass these gradients to our let's say 4 MLPs. Let's say we are taking 4 MLPs. So GA of K could be the number of hyperparameters, or let's say the number of MLPs you wanted to use, and then these MLPs will give you the updated gradients. and then you will basically update in your main model. So whatever the gradients you will be getting from here, you will be updating in your P of theta. And so basically the newer parameters will be responsible to give you the updated probability. Let's say Boris Johnson, the probability goes higher for this Boris Johnson. So this is the overall idea. Let's say you use this reading technique. So where you take gradients as your inputs, and then you pass it to your hypernetworks. Then this hypernetwork generate you the weights, then your gradients, and then you update in your main model. So this was the overall idea. So there are a couple of advantages. So let's say if you wanted to perform edits in your batches. So let's say you prepare a data set for these are the facts which are updated, and then you have this batch, and you can update update the information in a batch altogether. So this is like a kind of a good advantage. And then also you can scale over any kind of model. So let's say if you wanted to use some 7 billion models and you wanted to update the 7 billion, you can do it. If you wanted to update in your 70 billion, 80 billion, you can still do it. So, right, like these are the advantages. But one kind of disadvantages is, let's say this kind of technique uses a lot of data. So you need more data. And then again, the complexity was very high. So like these are the like follow-up works like which talks about the disadvantages of this kind of MEN technique. But again, like this is kind of uh, the one of the initial works, like which basically talks about, let's say, updating the factual knowledge in your model. Right. So one of the major disadvantage was the following. So let's say if you're performing this edit one by one, right? And you have, let's say, 10,000 of prompts which needs to be updated. And you will see, let's say after there is a threshold, and after you update, you reach that threshold, the overall performance for that model will start decreasing. So earlier, let's say earlier the accuracy was 90%. Then after updating, let's say 100 prompts, the accuracy will drop down by a significant margin. So this is how you can understand this disadvantage. So
Uh,
yeah, hi.
just yeah. So can you please explain that pipeline again, just briefly?
Right. So let's say you have this pre-trained model, which is like clear, and you have some probability for your given input, right? So probability for your weights, and then the generation, and XC could be your the input prompt. So let's say you were getting this, let's say 20% probability for Boris Johnson and 80% for your Theresa May, right? So what you will do is you will take the gradients. So let's say you are taking up gradients for your, so I'll tell you like in the later slides, like how do we do exactly. But let's say you take up 4 layers. So let's say you are having this BERT model. BERT model has 12 layers, right? And you wanted to update on the information, let's say layer number 8 to 12. So you take this 4 layers, let's say 8 to 11, something like that. So let's consider the indexing starts from 0. And you take this 4 layers, you take the weights, and then you pass those weights to your let's say the MEND architecture, or let's say my MEND architecture. I'm not going into mathematics, but you take the weights, and then this kind of MEND will be responsible for generating the newer weights. And whatever the newer weights, the newer matrices you will be getting, you will be directly going, let's say W1 is responsible for generating the weights for your layer number 8. Then you will be directly going to that layer number 8, and whatever the weights were earlier available, so you will be directly, let's say, subtracting, like element wise subtraction. And whatever the updates you will be getting, you will just pass the newer prompt, and then whatever the probability you will see, like the probability increases for Boris Johnson. So something like
Yeah,
that. I will
yeah, yeah.
I
So
can help you with resources if you want.
yeah. So that delta W and W2 WK,
Right,
which are responsible for Johnson. So how
right,
to
right.
identify them?
This,
Means how did you identify 8 to 12?
right, right. So in our work also, so we tried out with different set of layers. So what we do is, so this hyper network, so this is again, you don't have the precise control in this MEND kind of architecture. So if I come back again, so MEND comes over here, meta learning. So you don't have the exact control, like which layers to edit. So that's why in our work also, we tried out with initial layers, we tried out with the middle layers, and then we tried out with a different setup, let's say the last layers. And we also choose, let's say, random set of layers. So where exactly this information is stored exactly. But if you look in the newer kind of techniques, locate and edit, so this will give you the precise control. Let's say you should be going in the layer number 7 and onto the MLP number XYZ. But these kind of hyper network kind of approaches do not have the precise control.
Okay,
But these
so
kind of
is
techniques.
it is it like that guided back propagation thing where we
Hmm.
means backtrack the most activated neurons responsible for this
Uh,
classification?
Not exactly. So we just, let's say, we empirically we found out that layer number, let's say, for the middle layers, the most of the information was present in the middle layers, or let's say in the last layers. So we tried out with different kind of layers. So it's like all empirically we try to find out.
Okay, so you are not backtracking or
No, we are not backtracking.
okay, okay.
Yeah. So I'll tell you in our work, so how we did it. This is the work. So the title is the cross-lingual model editing in the multilingual models. So these kind of editing techniques were already existing in the NLP community. But where was it lacking? So we found out, so let's say if you wanted to update any information in one language and you wanted to check whether the information is also updated in the different language. Right. So so consider this kind of pipeline we followed. So let's say earlier the Donald Trump is the president of USA and the model says yes, support. So we tried out on the classification. So let's say we just had two classes, support and refute, and support says, let's say Donald Trump is the president, right? And you pass the again the prompt in, let's say, in Devanagari, in French, or in, let's say, Bangla, and then the model was still saying support, right? So let's say if you wanted to update this information in one language, so here we updated the information in English, and we wanted to check whether the information is updated in different languages or not, right? So let's say we were earlier focusing on the monolingual kind of editing. So right now we wanted to, like, we edit in one language, and then we wanted to verify if the fact is also updated in different kind of languages. So let's say in Devanagari, French, and Bangla, right? So these updates should be reflected. So this is the problem or the newer paradigm we introduced. So this was like lacking in the previous works also. And so I'll give you the overall idea. So again, the overall idea remains the same. Let's say was the president of USA, the intuition remains the same. Let's say it was Donald Trump. Then you take the gradients, you pass it to your editing model. Editing model is nothing. So let's say here we are choosing the Bloom model, and the editing model could be, let's say, a serial connection of 5 feet forwards. And then you're just passing this, you're just updating the gradients from this smaller model. And then you update the parameters in your main model, and then you update the information. But so right now what we did was the following. So we tried out, so we basically explored the cross-lingual paradigm on the existing METs. So for the, let's say, fine tuning the knowledge editor, or let's say the MEND kind of architecture, uh, and over the Latin and Indic scripts. So let's say so all in all we choose the 6 languages. So 3 were the high resource languages, which belong to the Latin script, and 3 languages were from the low resource languages. So where we were having this Indic script. So for the Latin we choose the English, Spanish, and French. And for the Indic scripts we were having our, let's say, the standard Bengali, Gujarati, and Hindi. So we choose these languages and we tried out. So we run almost, let's say, almost like 10,000 experiments over 69 configurations. So we were having this 6 language pairs. We choose like 3 models, and then we were using this 3 METs. So this configuration gave us almost 10,000 experiments. And if you look in the main paper, so we have almost like uh, 10,000 experiments, and the paper length was around 50 pages or something. And so all in all, another set of contribution was like we gave us this evidence. So where the multilingual information is exactly stored. So let's say you have this BERT model, and in this BERT model, the Hindi information is present in the middle layer. However, for the same information, for the same knowledge, in English is present in the initial layers. So if you wanted to localize the facts depending on the language, so we also gave this kind of uh, let's say the insights, right? And then we choose over the encoder only models and the decoder only model. So we again in the next slide. So for the encoder models, we were having the mBERT and XLM and XLM-RoBERTa, and we for this decoder base we had the Bloom model, the 560 million, the base model. And for the Latin script, we were having English, French, and Spanish. For the Indic, we have Hindi, Bengali, and Gujarati. And Latin script, again, the proportion is very, very high in the pre-training proportion for these models. And the Indic script were having the lower proportion in these encoder and decoder models in the pre-training part. So what we did was, so we prepared the data set first of all, and we were having this fever data set. So fever data set is a classification data set where we have around 1 lakh sentences, 1 lakh prompts, and then the val and test sets were the following. And we use the Google Translate API to translate it to the another 5 different languages: French, Spanish, Hindi, Bengali, and Gujarati. Then IEA basically is the inter-annotator agreement. We are having a couple of annotators who basically verified that these are the translations are really good. Then we have the relaxed inter-annotator agreement. So again, relaxed means, let's say, we were not focusing on the semantics. We were only focusing on the, so we were not focusing on the syntax. We were only focusing on the semantics on the translations. So we prepared our data set and we were measuring on the generability and the specificity. So let's say सिर्फ president का जो information है सिर्फ वही update होना चाहिए, and not the, let's say, the capital of Malta is Medina, so this should not be updated. So we were only focusing on 2 different aspects. So we wanted to explore for portability also, but we are keeping it for the next paper. And so I'll just give you the findings which we found out. So some of the insights are following. So just look on this table number 1. So on the left section, you will see, so this is the mBERT model. So left over here, so this block. So this is the mBERT model, and then on the right, we have the Bloom model. And IL basically means the initial layers. ML is the middle layers, L is the last layers, and RL is the random set of layers. So let's say layer number 2, 7, 5, 8, something like that. Or let's say layer number 2, 7, 5, 11, something like that. So and on the x-axis, so let's say if you talk, let's say there was a fact in Spanish and we are updating the fact in Spanish, and we wanted to check whether the fact is updated in French or not. So ES is our editing language, and FR, so the French is our is the validating language, right? So we found out that 90% of the time, if you edit in Spanish, we'll get the knowledge updated in French also. So this was, let's say, one of the the overall the objective also for us. And we found out, so for the encoder based models, the majority of the information was present in the last layers. However, for the decoder based model, it was in the middle layers. So if you look in the overall, let's say the average score over this block, so this was much higher than the last layers. So this means, and we verified this information with the previous works also, and all the claims were supported in our support. And majority of the information is in the middle layers rather than in case of decoder based models. But for the encoder based model, it was in the last layers. And another, on different kind of editing techniques also this varies. So we found out, so let's say for this Bloom, so when we were using the MEN kind of architecture to update the model and to update the information, so we found out that the information was in the middle layer. But if you look in let's say the knowledge editor kind of technique, so the information somehow shifted in the last layer also. So this means, let's say, it is not necessary that the information is only the middle layer. It could also be possible that the same information is also, let's say, dispersed in a set of layers. So this was like another finding we found out. And this random layer, so again, like these gives us the best, this yields the better results. So in some of the cases, it gives us better results. But again, we found out that the last layers was more common in the encoder, and in the decoder based model, it was in the middle layers. Another kind of interesting thing was let's say we use this ROM kind of technique to localize the fact. So let's say there was a fact, let's say iPod Classic is developed by Apple. So we use the causal tracing, and you can read these images as following. So in the red plots, these are the attentions for the Bloom 650 million model, and in the green you have the MLPs, and in the purple you have the hidden states. And so you can read the following. So let's say on the y-axis, or let's say in this heat map, the y-axis basically represents the probability. So let's say the probability for Apple is somewhat higher over here, and I means, so you just read this image as, let's say, one by one, let's say row wise. So this row can be decoded as following. So you're passing the model only one token, and that is only I. And given this prompt, what is the probability for Apple? It will be very low, which makes sense, right? And second time, you will rerun the model again, and now this iPod is basically your input, and then you will try to see like where where the probability for Apple is coming or not. And if you found out Apple, so you will just report that probability. So this is how you're running, right? And if you see over here, so we pass the same prompt in different languages for Spanish, French, and Portuguese, right? And then you will see for hidden, so for attentions and for this hidden states, the probability actually increased. So the probability actually increased in Portuguese. However, this was not the case in English. So this means that a single fact can be present in different layers. So it is possible that the iPod was in layer number 5, but in Portuguese it was in the layer number 10. This is also possible. And it is like in the previous finding, we found out that the information is dispersed. So the information can be in a series of layers. So that is also possible. So again, the third finding was this monolingual editing, where we edit in English. So let's say given we edit in one language, and we also check whether the fact is updated in the same language. So English, better results, definitely, which ideally should make sense, right? But if you look in the decoder model, so for the Bloom, this was not the case. So the scores were very, very comparable. So 74 and 75. So it is not that significant, right? And if you look over here, so let's say Bengali and Bengali. So let's say Bengali and Bengali ki case mein the scores were 71%, and for Bengali and Hindi was 72. So this means let's say Hindi and Bengali is somewhat, so the model was storing the information in the same set of layers for both for both languages. So this is also possible, right? So again, like monolingual editing gives us the better results. And in case of XCB, so in our paradigm, we found out that if you look in the scripts, so if you look on the Latin script, the scores are very, very high. And on the Indic scripts, the scores are very, very high. But if you see, if you edit in Latin, if you edit in, let's say, Latin script, if you edit in French, and we wanted to verify in let's say, in Gujarati, right? So this means the like only 58% of the time the facts are actually updated in Gujarati. So this means the information was not, let's say the information is somewhat script dependent also. Ideally, that should not be the case, right? But ideally, we saw that that the the information was script dependent also. Again, this stands true for your and decoder based models also. So this was like another finding we found out. Then what we did was, so let's say, like we just questioned ourselves, like, are we really doing the fine tuning? Let's say is the pre-portion of the information which already exists in the model. So let's say the proportion, the language proportion during our pre-training will have some effect during the fine tuning, or will make some impact in the editing or not, right? So what we did was, so we were having this 1 lakh sentences. So we picked up almost, let's say, so we were having, I think 6 languages, and then we divided, let's say 1 lakh divided by 6. And so whatever the number of prompts we get, we created an equal proportion data set. And all the facts are equally present in, let's say, there are, let's say, 100 facts, and all the 100 facts are present in 6 different languages. And then we fine tune over this mixed kind of data set. And then we found out that the model was actually learning better. So this means, let's say, if you wanted to fine tune your model, the proportion of your languages will have some impact. And if you have the equal proportion, you will find out that the model will give you better results. So this is what we found out. And again, we found out that, say, if you look at the inverse proportion, so let's say English was the most dominant. So now in this case, if we say that the Bengali was the least, so we will just take the 1 minus, let's say 100 minus probability for English. And then this proportion will be represented to Bengali. So will this inverse proportion give us better results? But we found out that these methods do not give you the better results. But the major insight was, so this mixed kind of proportion will actually have better impact. And last finding was the following. So let's say, so what we did was, so we prepared this Hindi fever data set also, right? So let's say we picked up our models, and then we fine-tuned our models on the Hindi data set. And we were editing on our MEND kind of architecture. And we are also we find out on the Hindi. And if you look on the information, so let's say for decoder based models, for the encoder based models, the information was present in Hindi, right? So the scores are very, very high. But if you look over here, so Hindi is having very high correlation with Bengali. So this means that that model is somehow learning. So considering proportion, the model was having better correlation with the lower source languages. So if you have some language, uh, it will be highly likely that that editing will be very biased toward the same proportion or in the same script. So again, the script also matters over here. And if you so again in the paper we found out that if you fine tune on Gujarati and then so Gujarati was giving better results for the Indic scripts rather than for the Latin scripts. So this was the finding we found out. And if you look over here, so on the decoder based models, so while we fine tune on Hindi, the scores for Hindi got very, very high. So earlier it was, so in the previous slide, so the scores were not even closer to your, let's say, were not even crossing the 60 or 70%, 75% mark, right? But if you look over here, so the scores significantly increased to 90% to 85. So on an average, it was 92 or 90%. So this was like the last finding we found out. And talking about the limitation in future work, so again, like adding, so we are looking on this editing in the encoder decoder architectures, extending this work to the more languages and then for more tasks, so for generations, translation, and all other tasks. And also this again, that the login and edit is one of the like direction one should definitely be looking for. And I think I'm done with the slides. So thanks all. And if you have any questions, just let me know. Yeah, I'll be more than happy to answer. So yeah,
Hi, am I audible?
yeah, you're audible.
So I just had one question. Like I
Sure.
understood the editing part. So it basically we try to identify in a multiple way, like which set of layers may be affecting this particular text. We try to update
Right,
those and then see if it is giving the relevant information. Now let's
right.
say if we are working with a very large models, how do we
Hmm.
ensure that it is not actually affecting the other part, like other kind of text?
Right. So for that, so there's a library. It's not a library. It's like I'll just show you once. Yeah, so this slide. So this is a very nice paper from this Zhang. So again, I don't remember the venue, but it recently got accepted to, I think in EMLP or something, not this year or last year. I forgot. So they were actually ensuring this kind of technique using this portability. So portability, let's say if you wanted to update the depending facts and the specificities, let's say the actress, like so who plays this role on on this series or something. So you basically measure that it is not hurting the other performance, right? So
Okay.
you have this matrix, and again, locate and edit is something like people actually is looking for, because this will give you the exact the will give you the more confidence. So the information which you don't want to update will is basically preserved. Understood?
Oh, yeah, got it, got it.
Yeah.
So only by testing you will come to know that it is not disturbing the other thing.
Yes, but so there's a very recent paper. So I think last year में Rome का एक paper आया था. So this technique of Rome. So you can look in this paper. They talk about the causal tracing. So before even we start editing, we can look like where this information is actually present. And once we localize that information, then we can proceed with the editing part. That is also possible. But
Yeah.
I think you should be looking in this Roman method papers.
Okay.
Yeah.
So my question, so the first thing is I would like to say that this findings that you showed is very interesting. The
Thanks.
layer locating the things and all. So
Right.
and like so, how did you find that those metrics? Like you tested all the experimentations of the metrics?
Yeah. So what we did was, so maybe I can show you the paper also. I think it's better if you go in the paper itself. So this is the paper, and I hope like my like the paper is visible.
Yes.
Yeah. So this was the huge paper like I was talking about. So like a lot of experiments. So we were having the number of experiments actually crossed uh our like say हमारी idea में भी नहीं था कि like this will cross this much, and we evidently we ended up adding an index table for the results. So for this type of editing technique, for this model, for this language, you should be going in this table. So the number of experiments exceeded our expectations, and so if you look over here, so these are the two tables which I wanted to highlight. So again, for left में ये जो BERT वाला model है, and on the right we have the Bloom model. And similarly, so this is one of our GS. GS is the generability. कि जो हमें the facts which we wanted to update. And this, so let's say if you're talking about Spanish and French, so this 90% chance. So what we did was, okay, we created a test set where we had around 1200 samples. And from this 1200, we wanted to check whether these 1200 fringe sentences are actually updated. So we saw that 90% of this 1200 sentences or the phrases actually got updated. Right. So,
Okay.
and
Yeah.
for this, if you talk about the specificity. So specificity is again the same, the facts which we don't want to edit. So we had this test set where we were not having this 1200, which actually we were using to edit. Right. And over here we reported, let's say, the fact which we don't want to update is actually is as it is.
Okay, so can you just mention again what is this probability indicating? Means when you change the French, whether sorry, let's say if you change English, whether the French is getting changed.
Yes.
That is right. Yeah.
Yes. 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 So let's say if you are updating, so let's say consider the breakdown, like I can break down this table as following. So on this left side, so this is the mBERT model, right? And I'm only updating, let's say, layer number 8 to 12. And while updating the layer number 8 to 12, I'm using Spanish. I'm having some prompts in Spanish. And I wanted to check whether, let's say, I have this data set of 1200 and these 1200 sentences in French are updated or not. So I will just like edit and I will check, let's say 90% of the time it was actually got updated.
Yes.
So this is the breakdown. And again, for the specificity, so 98% of the time, the facts which we don't wanted to update were preserved, but 2% of the time, जो हमें fact like which we don't wanted to update actually got updated.
Okay.
Understood?
Yeah.
So let's say Bengali and Bengali. So let's say we were updating some fact in Bengali and Bengali में हम check कर रहे थे. So this means like 29% of the time fact जो update नहीं होने चाहिए तो वो update हो चुके हैं. So this is how we can break it down.
Okay.
Right? Yeah.
So it's kind of a lot of experimentations you did.
Lot of experiments.
Yeah.
So if you see over here, so I think our lot of experiments. So we evidently we ended up creating this index table just to keep track of all the tables. So if you look over here, so just tables, that's it. These are just the results. So this was a very huge paper.
Great. This is a very useful work for many of the low resource languages people who are working.
Right. Right. And also for the interpretability part also, because definitely these techniques use interpretable.
Yeah, because most of the people are unable to interpret the LLMs.
Yeah. Right. Yeah.
Thanks.
Yeah, thanks.
Okay, if there are no other questions, then maybe we can thank the speaker for the wonderful talk today. And yeah, so thank you so much, Himanshu,
Yeah,
for
thank you
giving
so
your
much,
time and
Siddharth.
for this talk.
Yeah.
I'm going to stop the recording now.
Sure.
And